This conference will now be recorded.
Hello, everyone, and thank you for virtually joining our presentation for today. I am Hassam Alisa from Microsoft Data Center Advanced Development Team, along with my co-presenters, John Fernandez from Facebook and Cam Turner from Cool IT Systems. Today, we will be talking about air-assisted liquid cooling. As part of OCP Advanced Cooling work streams, this session will be focused on Coldplate enablement using air assist. So basically, for the case where the end user wants to use Coldplates to support certain chip flux or rack density goals, but they may not have liquid or facility water available at the data center level. So what's driving the industry to require Coldplates or liquid cooling in general? We are seeing increased chip fluxes, the CPU and the GPU and the FPGAs, sometimes accompanied with reduced case temperature, increasing the thermal challenges. And we will touch on that in more details. But in the light of the fact that most of current hyperscale DC designs have been optimized to be most efficient and cost-effective using air cooling, we have to be cognizant that not all application might require those higher flux chips. We might end up with a mixed low flux and high flux chips throughout the facility. So we need to make sensible TCO-driven decisions. Whether do we need water throughout the DC or locally where needed, or what we will be showing you here today, which is the use of air assist water cooling. There has been a lot of work, thought, and investment into optimizing air-cooled data centers. As we moved from chiller-cooled DCs with higher mechanical overhead to introducing economizer hours and trim chilling, and even getting further into free cooling, whether it's indirect or direct-based evaporative cooling. Through those optimization efforts, the PUE has been going down, the water consumption as well as the cost for those air-cooled data centers. And of course, new challenges arose as well, such as effect of when introducing free cool to the data center, effect of particulate contamination, and also the need to dampen the effect of sudden change in weather profiles. But the question is here, for those efficient existing air-cooled data center, how can we enable liquid cooling with them or in them efficiently and enable liquid cooling chips? Air-assisted liquid cooling is an intermediate step to use the data center air to cool the water coming to the chips without the need of facility water, as you can see in the center image. Eventually, and if needed, and if that's dictated by this queue, we just might move to data centers equipped with water support, potentially even using dry coolers, for example. Next, John Fernandez from Facebook will walk you through details on case studies and specifications.
All right, thanks, Sam. Good afternoon, everyone. My name is John Fernandez, and I am a thermal engineer in Facebook's hardware engineering team. So as a preface to the air-assisted liquid cooling effort, the first step was conducting a case study to understand the true benefits of enabling closed-loop liquid cooling in an air-cooled facility. In this case, a very quick project involving liquid cooling GPU shelves in an open rack V2 was conducted. Here, the liquid cooling loop is created by the GPU shelves or the cold plates in them, along with rack level manifolds, a rear door heat exchanger, and a modified CDU to drive the coolant closed loop. So the heat that was absorbed by the cold plates that were attached directly to the GPUs was exhausted by the rear door heat exchanger through the air that was exhausted by the IT gear approaching it. As you can see, this forms a closed loop solution, and therefore the rack is 100% air-cooled. Please note in this image that the manifolds are not shown, as it's hidden by the adapter frame that the door heat exchanger was mounted to. And the other load inside the rack that was 100% air-cooled, such as the compute sleds and blanking panels, are not shown here. So extensive testing of this rack level setup involving GPU sleds showed that when employing air-assisted liquid cooling, or with the system that was assembled as shown in the previous rack, that for a given airflow rate, this closed loop liquid cooling solution delivers much promise in the form of 50% higher power consumption support as compared to the original air-cooled solution. However, further improvement in cooling components could push these projections even further. It's important to note that this case study was employed off-the-shelf components and required a few workarounds. So as such, there were some inherent trade-offs that had to be made. However, if these components that form the air-assisted liquid cooling solution could be streamlined and a system is formed more intricately, we would deliver a more robust solution. So there are existing efforts within the ACS subgroup under Rack and Power that could be leveraged to enable the same. Like, for example, the door heat exchanger subgroup. So in the ACS door heat exchanger subgroup, the community is working on defining a specification for the rack-mounted solution. There are many areas of focus as outlined in this slide, and a lot of these can be leveraged for air-assisted liquid cooling needs. So some of the areas include the physical requirements, such as dimensions, weight, the physical interfaces for coolant, power, and communication. Other areas such as reliability and quality focus on manufacturing level tests that can be conducted on the assembled solution to ensure that the components are leak proof, as well as rack level implementations or ensuring that the airflow within the rack is sealed so that both the door heat exchanger and the rack form a seamless solution. Next, we will go over a couple of areas. From a performance and metrology standpoint, requirements have been outlined which conditionally apply to the type of door heat exchanger, whether it is a passive type or an active variant. These include fan redundancy, test standards and reference conditions that the supplier can use to evaluate the cooling capacity based on predefined conditions as outlined in the specification. And also design and solution targets to minimize the impact to the IT rack and the facility. So over here, you can see a couple of areas that are defined from an air standpoint, which is both pressure drop for a passive cooler, as well as an active cooler, targeting really efficient performance, such as the power consumption being less than or equal to 2% of the rated heat rejection capacity. And from a coolant resource standpoint, defining the pressure drop limitation and also the coolant supply pressure conditions that the solution would need to overcome. So these are areas that could be directly leveraged to enabling air-assisted liquid cooling. Another section of the specification is monitoring and control. To ensure effective and efficient operation of the door heat exchanger, Sensors and control represent valuable implementations or additions to the system. So as can be seen in this slide, sensors are outlined and categorized as either required or optional, and also further categorized based on whether they apply to a passive or an active variant. Similar definitions for alarms and control are included in the specification, as is the OCP guidance for hardware monitoring. A Redfish mockup is currently being prepared for review by OCP stakeholders as well as DMTF contacts, with the goal of confirming these definitions as well as subparameters and contributing reference files and documentation, such as a schema or JSON file, as well as a reference guide that outlines how to use those files. This is another area that can be directly leveraged for air-assisted liquid cooling. So moving back to the air-assisted liquid cooling system as a whole, it's fairly clear based on the case study that this system can be outlined in the slide on the right-hand side over here, and how different components form a system to generate above ambient temperature coolant for liquid cooling needs. It also outlines how subcomponents can be optimized to avoid redundant features. For example, the RPU is basically a CDU without a plate heat exchanger. And in the air-assisted liquid cooling concept, this reservoir and pumping unit serves as the hub of the air-assisted liquid cooling system by powering and controlling the remote liquid-to-air heat exchanger. So in this way, unnecessary overhead that would be involved in using off-the-head components can be minimized, and the system becomes more flexible or modular. So this remote liquid-to-air heat exchanger could be a door heat exchanger, could be an adjacent rack cooler for higher capacity, or an in-rack heat exchanger solution if space in the rack is available. Therefore, the liquid-to-air heat exchanger portion of this solution becomes flexible and can be optimized for performance or the end use case. And the RPU, being the hub of the solution as described before, can be standardized and optimized and also be designed for interoperability to enable multiple solution providers to support this product. Next, Cam Turner will outline details of the RPU.
Thanks, John. Hi, folks. My name is Cam Turner, and I am the Director of the Hyperscale Solutions team at Cool IT Systems. As John mentioned, the concept of the RPU came from the initial case study where we modified Cool IT Systems CHX80 rack-based liquid-to-liquid CDU to meet the design targets. Having proven that concept, we needed to optimize the design for hyperscale. This included support for both the open rack and 19-inch EIA architectures. So this was done by optimizing the design around the smaller form factor of the 4U 19-inch rack, and then creating an adapter frame that would fit within the larger space of the open rack V3 and V2 frames. As always, cost optimization was a requirement, so we removed all non-essential components ranging from the heat exchanger to the touchscreen interface. To support interoperability between vendors, standardization for electrical and liquid interfaces is required. This includes not only the type of connector, but also the locations, just to make sure that there is no crashing with any other components in the system. And when you swap out components, you don't run short on cable or tube length. Interoperability also requires standard reporting interfaces to the rack manager and to the DCIM level. This effort will continue, and it will be a collaboration with the other applicable OCP work streams. To support the reliability and resilience required by hyperscalers, a version of the RPU was designed with hot swappable pumps. This required extensive joint R&D efforts between CoolIT and our friends at Staubli to design dry break QDs capable of the required flow, misalignment tolerance, and reliability requirements for this product. We also worked with our friends at GRI Pumps to develop a pump capable of the flow and pressure requirements for the AALC solutions. And of course, they needed to fit within the space constraints of the RPU. To support both Open Rack and Project Olympus racks, a DC variant and an AC variant are included. The DC variant will provide power to the remote liquid-to-air heat exchanger in order to prevent the need for the hex assembly to plug directly into the bus bar. And as John mentioned, the RPU is the brains of the system, so it needs to be able to control the internal pumps for the liquid as well as the fans on the remote liquid-to-air heat exchanger. The flow performance target for the RPU is 20 to 70 liters per minute. On the upside of this, that accommodates a maximum of 2 liters per minute per kilowatt on a 35 kilowatt rack of IT gear. The overall power consumption for the cooling solution is targeted at equal to or less than 5% of the rack IT power. So in other words, for a 35 kilowatt rack, the RPU and the liquid-to-air heat exchanger must consume less than or equal to 1.75 kilowatts. All the telemetry necessary for control and failure detection will either be included natively within the RPU or have an interface to the sensors in the remote liquid-to-air heat exchanger. Internal sensors include coolant temperature, pressure and flow, reservoir level, leak detection, power consumption, and pump speed. While the external sensors include fan control and tachometer reading, air temperature sensors for the cold aisle air temperature, as well as the coil on temperature and the coil exhaust temperature, and delta pressure across the coil. To test the AALC concepts, CoolIT collaborated with our friends at Coolterra to design both an adjacent rack and a rear door heat exchanger based system. On the left-hand side of the screen, the adjacent rack liquid-to-air heat exchanger is CoolIT Systems Rack DLC AHX35. This is a modular solution comprised of the RPU and a 35 kilowatt liquid-to-air heat exchanger mounted inside an open rack V3 frame. The bottom 4U are occupied by the RPU. There are 10 efficient 200 millimeter fans with N+2 redundancy, and the target approach temperature of this heat exchanger at 35 kilowatt heat load is 10 degrees Celsius. Now, the 35 kilowatts can come in the form of either one high density rack as shown in the photo, or 2 lower density racks, both connected to the RPU in parallel. On the right-hand side is the rather sharp-looking Rack DLC AHX40 in Project Olympus White. This is a modular solution comprised of the RPU, a blind mate vertical rack manifold, and a 40 kilowatt active rear door heat exchanger. The bottom 4U are occupied by the RPU. It has blind mate power and liquid connections, and there are 5 efficient 280 millimeter fans with N+1 redundancy. In this solution, the target approach temperature is 12 degrees C with a 40 kilowatt load. With that, I'll pass this back to Sam for a comparison between the two solutions.
Thank you, Cam. So both the rear door heat exchanger and the adjacent rack cooler solutions are great enablers for liquid cooling and air-cooled facilities where we don't have facility water. Here we're going to make some commentary on some of the main characteristics of each solution. From an airflow perspective, especially in a containment environment where the CFM budget is limited, in the rear door heat exchanger option, the same amount of airflow is used in the IT, and it will be used to cool the water in the rear door heat exchanger. However, in the adjacent rack cooler system, some extra CFM budgeting will be required since the heat exchanger airflow and the IT airflow are separate streams. Looking at the IT preheat point of view, the rear door heat exchanger case, the coils will experience higher air temperature due to the IT preheat. That might stress the system to reach certain required water temperatures, while the adjacent rack cooler system does not have this challenge since it only ingests fresh air. From a serviceability perspective, especially when doing rear or hot aisle serviceability, opening the rear door heat exchanger can affect the system water temperature. So this is a point that operator need to be cognizant of when operating these systems. From a deployment point of view, the rear door heat exchanger enables rack and roll fully integrated systems. So the rack, the IT, and the rear door heat exchanger as one system, while the adjacent rack cooler requires dealing with two separate rack entities. From a flexibility perspective, the adjacent rack cooler is more flexible since it can even be used to enable further liquid cooling technology, such as enabling an immersion tank in an air-cooled setting. From a space point of view, obviously, one extra tile or space unit will be needed for the adjacent rack cooler. And finally, from a control point of view, the rear door heat exchanger system might be more involved since from a control point of view, since the system has to satisfy both the IT airflow supply as well as the water temperature requirement. As we get to the call to action slide, we want to highlight that this Air Assist workstream is a fruit of OCP's Advanced Cooling Solution work threads and work streams. So big kudos to those teams. So now we want to talk about how can we work together through OCP to streamline this technology. And we can start with standardizing heat exchangers, manifolds, pumps, and coolants across the supply chain. Also by having consistent guidelines for deployments, serviceability, and control methods and telemetry requires of these systems. And finally, by addressing the uniform methods or agreed on methods on leakage and risk mitigation for these systems. Finally, please check out these links below to see all the great work being done by the OCP Advanced Cooling Solution work streams on enabling liquid cooling. Thank you very much. That concludes our presentation. And now we will open the floor for questions.
Hi everyone, this is Cam Turner. There's a question regarding how do you avoid water leaks in the rack as well as in the CDU. Excuse me. So this is done through just fundamental engineering and design to ensure that there's reliability of the system. That's done throughout all of the individual components, ranging from the CDU or the RPU, the rear door as well as the tubes and the QDs. There are separate OCP work groups that are working on suggesting ways of testing all the individual components, as well as there is a work stream underway to determine the best way to do integration testing for the entire system.
I think we can also highlight that the ACS Coldplate stream is currently looking to put together a white paper on that very topic. So that might be something for people who are interested to follow up on. Thanks, Cam.
Hey everyone, this is Hassan from Microsoft. I wanted to we had a question talking about water pressure, negative pressure, and leakage mitigation. So I just want to provide some general commentary. Generally speaking, with single-phase PG25 or water-style systems, we look into ensuring that fittings and pipes and the components of the loop are qualified for higher operating pressures than the typical norm that would run on a daily basis. But I saw some comments on negative pressure, so we're also open to concepts of negative pressure, negative displacement pumps, or even dielectric fluids that could even mitigate further. So I just wanted to provide commentary on that question.
There's a question on 35 kilowatts being the largest option being sold. The 35 kilowatt rating is based on what we would deem efficient use of air. If you could get more airflow through the system, you certainly could go to higher than 35 kilowatts. At this juncture, that's what we've been focused on, though.
Yeah, so to add to Cam's point, I guess that's also a trade-off between how much of a budget do you have at your data center, and also, you know, going to a higher capacity would, in a given form factor, would require you to push more airflow, which would also call into question how efficient the design could be. So I think to Cam's point is it's sort of a balance between these different parameters or boundary conditions that can sort of bring us to a target that's fairly efficient, but can also take care of a relatively reasonable cooling capacity. I think there's a question with regards to the 35 kilowatt rating and what temperature delta does that require. I think we can answer that on 2 points. One is on the air side, that 35 kilowatt rating is based on a higher delta T on the air side to exhaust the heat from the liquid to a heat exchanger. So anywhere between 15 to 20 degrees. If the question is more on the coolant side, that is more along the lines of around 10 degrees C. Anyway, the different demo units that were outlined in the presentation, you know, please feel free to visit either the Facebook or Microsoft booth, and there'll be videos over there outlining more details. So hopefully that will help answer a lot of questions that a lot of our attendees have with regards to that. Thanks.
There was a question about moving to row-level CDU technology. I mean, that is definitely the natural next step through the progression into liquid cooling for cold plates. But this presentation has been focused on enabling liquid cooling on the chip in air-cooled facilities.
All right, I think that's all the time we have. Thank you all for attending the presentation, and feel free to reach out to us offline if you have any other specific questions. Thank you.
Thank you very much.